Hello everyone, I'm Aniruddh Vashisth, Assistant Professor at University of Washington, Seattle, and today I will be telling you about a new combined atomistic continuum model that we have developed to examine interfacial fracture in multilayer ceramics. This work has been done in collaboration with Professor Mir Mulad Mesier at Florida Institute of Technology. Multi-layer high-temperature ceramics have found applications ranging from high-power electronic systems in electrical engineering to shielding materials in aerospace engineering. These materials can perform in severe conditions such as high temperature and corrosive environments. A crack or a defect initiated at the interface can result in residual mechanical and thermal stresses and possibly catastrophic failure. To understand the interplay between the ceramic material chemistry and the fracture properties, we developed a combined atomistic continuum model that can help understanding the interfacial properties of this type of composite. We chose SiC-SiO2 composite as the model system. Ceramic composites with SiC-SiO2 interface find applications as microelectronics and semiconductors. However, like other bonded components, performance challenges are inevitable due to high density of defects existing at the interface of the SiC-SiO2 composites. Like other SiC-based bonded components, SiC-SiO2 interface is considered a strong interface, where the interface crack tends to propagate through one of the base materials instead of growing through the interface. Working on this problem, one of the main questions that we had in mind was, can we capture effects of temperature on interfacial fracture behavior as well? I will start off by showing you the time-distance landscape for simulations. Atomistic simulations can be carried out using either quantum mechanics simulations, where only few atoms can be simulated, or force field methods that can simulate larger systems but are not as detailed as quantum mechanics calculations. ReaxFF bridges the gap between quantum mechanics and force field methods, as ReaxFF can simulate dynamic events for large systems. ReaxFF is a reactive force field molecular dynamics simulation technique that uses the bond order concept to consider the instantaneous interactions between atoms. It provides a smooth transition between the non-bonded states and the bonded states, allowing one to investigate ongoing chemical reactions where bond formation and dissociation are involved during temperature simulations. In this investigation, we developed a framework to use the temperature-dependent thermomechanical properties derived from ReaxFF simulations in a continuum fracture model. To do this, we virtually fabricated and carried out mechanical testing of SiO2 and SiC specimens with at least 8,000 atoms. You can see the specimens during mechanical testing at 0, 1.5, and 3.5 strain. Using reactive force fields, we calculated the modulus, strength, and Poisson's ratio for these two ceramics that we input in the continuum model. The virtual mechanical testing was carried out using lamps. Here are the simulated properties of SiO2. A representative stress strain and longitudinal versus transverse strain can be seen on the top left. Intuitively, we see that the modulus and the strength decreases with increasing temperature and Poisson's ratio increases with temperature. We compared these properties with experiments reported in the literature and found good agreement. We also calculated the modulus, strength, and Poisson ratio for SiC ceramics. Interestingly, we see that the modulus decreases up to 700 Kelvin but plateaus between 700 to 900 Kelvin. The strength decreases monotonically. Poisson ratio also plateaus out after 700 Kelvin. Next, we transition into looking at the continuum model, and I will not write down all the equations for the model, but highlight some of the important parameters and equations for you. The constitutive equations were determined with the goal to develop fracture curves at different temperatures. We first calculate the bimaterial constant, where the equation is given here, which is an important parameter in interfacial fracture analysis relating material properties of each base material to the interfacial crack growth. Having known the effect of ambient temperature on elastic modulus and Poisson ratio of SiO2 and SiC, The bimaterial constant can be obtained as a function of temperature as shown in the figure. As the ambient temperature increases, bimaterial constant decreases generally. However, a local increase is seen between 700 Kelvin and 900 Kelvin. Such a local increase is rooted in the variation of Poisson ratio and elastic modulus of SiC that we discussed in the previous slide. At these similar temperature ranges of 700 to 900 Kelvin due to reactive effects that were captured using ReaxFF. Before getting into the fracture curves, let me quickly introduce Mode 1 and Mode 2 types of fractures. Mode 1 is the opening mode of fracture with a tensile stress normal to the plane of the crack, whereas Mode 2, as you can see here in the slide, is the sliding mode where a shear stress is acting parallel to the plane of crack and perpendicular to the fracture front. With this knowledge, we next look into kinking angle versus mode mixity. Kinking is when the propagating fracture deviates from its path and in this case moves from the interface into one of the materials, that is SiO2 or SiC. The strong bond at SiC-SiO2 interface leads kinking of the interface crack under mixed mode loading conditions. The crack kinking happens not only because of the asymmetrical loading, but also because of the differences in the material properties at the interface due to the Poisson's effect. However, for the first time, the effect of temperature on the kinking angle is evaluated computationally in this work. As shown, the temperature effect is maximized under Mode 1 dominant mixed mode condition, while having no effect under pure Mode 1 and pure Mode 2 conditions. And finally, we look at the fracture curves generated by this combined atomistic and continuum model. The temperature also affects the interfacial fracture toughness in the full range of mixed mode conditions from pure Mode 1 to pure Mode 2. As the temperature increases, the interfacial fracture toughness decreases due to low energy required for breaking the interface bonds. It is seen that as the ambient temperature increases, the mixed mode fracture toughness decreases. It is also evident that the temperature dependency of the mixed mode fracture toughness is maximized at pure Mode 2 and minimized at pure Mode 1. You can see 57% and 75% reduction at pure Mode 1 and pure Mode 2, respectively from 300 Kelvin to 1200 Kelvin. In conclusion, we demonstrated an atomistic continuum model that can be translated to generate fracture curves for multi-layer ceramics if the chemistry is known to us and we have a well-trained ReaxFF force field. Thank you so much for your time. Please feel free to email me at vashisth@uw.edu for any queries, or feel free to contact me on the MRS forum. Thank you so much.